Okay, so I'm looking at the chapter review first question. They kind of give you a lot of details here. It's not a big mystery that this is going to be a chi-square goodness of fit, right? They tell you the ratio should be 1 to 2 to 1. And then even explain it a little bit, make it easier to say, look, 1 to 2 to 1 means 25% will be green, 50% yellow-green, 25% bino. They take 84 randomly selected pairs, so that's your sample size, right? And then here are your observed counts, 23, 50, and 11, okay? Do they provide convincing evidence? So I'm going to focus more on the mechanics, but remember your conditions for inference here. We need to have a SRS. It does say that the pairs were randomly selected, so we're good on that. All the expected counts have to be bigger than 5, so we'll check that in 1 second. And we don't want this 84 to be more than 1/10 of the whole population, so we're probably good on that as well, right? And 1% level. So the null hypothesis is going to be that these offsprings do follow the expected ratio, right? They follow it, closely enough. It doesn't have to be exact, but so the null hypothesis would be that they follow the expected ratio. The alternate would be that at least one of them is different. And in the null and alternate hypothesis, try not to talk about your expected counts, and that starts sounding like a sample. Make sure you're talking about the population. But these 84 offspring are a random sample of the whole population, so we want to say that this population that these 84 were taken from follows those expected counts. Or the alternate would be that at least one of them does not follow the expected counts. So I think you told me you have an inspire, so I'm going to use my inspire here. For chi-squared goodness of fit, we go to a spreadsheet. Okay, all we really need for this is a couple of lists. All right, so I have my, I'm going to call this list the observed list, and this list I'll call the expected list. You call it EXPP because it looks like EXP means something, and so does. Alright, so hopefully I get away with these two types of lists here. So let me jump back there and see what those observed counts were again. They were 23, 50, and 11. Right? So we have 23, 50, and 11. Okay. And then our expecteds are going to be what? This one was supposed to be 25% of 84. So 0.25 times 84, I get 21. And then we had 50% of 84, 42. And then I think another 21. Okay. So we can see the expected counts and observed counts are not exact, but the idea of chi-squared is to test, are they significantly different from each other? Okay. So I'm going to go menu, number 4 for statistics, stat tests, and let's go find chi-square goodness of fit, number 7. My old calculator yesterday didn't have it. So my observed list, I'm going to click in here. That's the one I called OBS. Expected list, I called it EXPP. And degrees of freedom, remember this is number of categories minus 1. So we have 3 categories minus 1, that'll be 2 degrees of freedom. Okay. We click OK, and we are good to go. We get a chi-squared statistic of 6.476, p-value 0.039. So at 1% level, right, if alpha is 0.01, we'd fail to reject the null hypothesis. We don't have convincing evidence that this population doesn't follow that genetic code offspring. Okay, so you can always, you don't have the online book, but I think if you have your textbook, you can look these answers up in the back. But you can take a look at that and see right from our calculator. Calculator does all the heavy lifting for us, but you do need to remember some of those basic setups. All right, so that's chi-square goodness of fit. I'm going to try to put together a test of independence or association, and then also a homogeneity test. We looked at some of those multiple choice wise yesterday, but hopefully this is helpful.